could shut down a city, if they could neutralize all magnetic fields. For the moment, however, this is only science fiction. But how would everyday life differ if the principles of magnetism had not been discovered? Well, for one thing, cars as we know them would not exist. There would be no electric starter, no headlights, and most important of all, no radio. There'd be no electric lights or anything else that runs on electricity from conventional generating plants. Without elevators, only the fittest would want to live above the third floor. So skyscrapers wouldn't exist. Fortunately for us, magnetism was discovered. As early as 550 BC, the Greeks knew that a naturally occurring mineral called magnetite or lodestone had a mysterious attraction for iron. They called the lodestone a magnet because it was originally found near Magnesia in Turkey. By 1050 AD, it was known that a piece of lodestone suspended in the center would gradually swivel until it pointed in a north-south direction. Soon sailors were using lodestone for navigation. Early compasses consisted of lodestone attached to a piece of wood, floating in water so that it was free to rotate. These mysterious pieces of stone advanced sea exploration as never before. But there are other developments. In 1269, the French crusader Petrus Peregrinus chiseled a sphere of lodestone. When he sprinkled iron filings on the sphere, he found that the filings arranged themselves in lines. These lines connected 2 points on the sphere, which he called poles. The lines formed by the iron filings indicate the north-south orientation of the magnetic field. So a compass placed anywhere on a lodestone sphere will align itself with the magnetic field. The magnetic field around a magnet can easily be seen by placing a piece of paper over the magnet and sprinkling iron filings on it. Gravity restricts the filings to the flat plane of the paper, and friction keeps them from moving towards the poles of the magnet. In space, however, with almost no gravitational influence, the pattern formed by the iron filings takes on a new shape. The true three-dimensional nature of the field becomes clearly evident. But without the force of friction, the iron filings quickly migrate to the poles. During the 1500s, compasses became more and more elaborate. But explorers still believed that there were huge mountains of lodestone in the Arctic, which attracted compass needles. In 1600, William Gilbert, a British scientist, concluded that the entire planet was a huge magnet with a vast magnetic field stretching between the 2 poles. But which magnetic pole should be found at the top of the globe? We know that the north pole of a compass points north. And we also know that opposite poles attract. Therefore, since the magnetic pole in the Arctic attracts the north pole of a magnet, the Arctic pole is actually a south pole. And the magnetic pole in the Antarctic, a north pole. Ever since the arbitrary naming of the poles as north and south, the poles of all other magnets have been identified accordingly. It is for this reason that the Earth's Arctic pole is considered to be the south pole of a magnet. In further experiments, Gilbert heated a magnet until it became red hot and discovered that it had lost its magnetic properties. The interior of the Earth with its molten core is extremely hot as well. So we know that it should not function as a large magnet. Yet, the magnetic poles definitely exist. One theory holds. It is the electrically conducting liquid iron core rotating relative to the mantle that provides the north-south magnetic field of the Earth. But these magnetic poles do not coincide with the geographic poles of the Earth. The geographic poles are simply the two endpoints of the axis about which the Earth rotates, and are not directly related to the magnetic poles. So, depending on where you live, the angle between true north and magnetic north may differ significantly. For instance, if you live in Eureka, in the Northwest Territories, the angle between true north and magnetic north is 98 degrees. As far as we know, Christopher Columbus was the first to detect small variations in compass readings at different locations as he sailed westward. He determined the northerly direction using the sun and stars, and then compared this to his compass direction. To his dismay, over a period of many days, the variation between the compass readings and the stars gradually changed. But fearful that his men would want to turn back, Columbus kept this knowledge to himself. The variation between magnetic north and true north is known as magnetic declination. In Toronto, the magnetic declination is 9 degrees west of north. In Churchill, Manitoba, the declination is 0 degrees, because a line passing through the magnetic pole and the geographic pole also passes through Churchill. However, the declination for a specific place does not stay constant because the location of the north and south magnetic poles is not fixed. Another significant feature of the Earth's magnetic field is its orientation to the surface of the Earth. It is only at the equator that the field is parallel to the Earth's surface. At all other locations, the field is inclined to the surface. The angle between the Earth's surface and the magnetic field is called the angle of inclination. The angle of inclination is measured with a special compass called a dip needle, which allows the needle to pivot vertically. Exactly at the magnetic poles, the field is perpendicular to the surface. Obviously, this creates a major problem when navigating in polar regions with a magnetic compass. And this is one time when knowledge of the Earth's magnetic field can have you going around in circles. When you're out on the water, it's great to be fishing. But fog does tend to dim your enthusiasm. Don't despair. Your handy compass works in rain, hail, and yes, even fog. Unless, of course, there is something which throws the compass off. In which case, you might be in for a bit of a surprise. A compass needle is simply a magnet, and an attractive force exists between magnets and iron objects, even at a distance and even through the vacuum of space. It's as if invisible hands pull the magnet and metal together. In this way, magnetism is similar to the forces that charged particles exert on each other. These forces act over a distance in the same mysterious way. During the 17th and 18th centuries, electricity and magnetism developed as separate sciences and were believed to be unrelated. Then, in 1800, Alessandro Volta developed a device that paved the way for a change in this view. His device consisted of copper and silver coins, arranged in a column and separated by pieces of cardboard soaked in salt water. When he attached a conductor to the top and bottom, like this, and brought the two ends together, a spark resulted, indicating that a flow of charge was occurring. Volta's work eventually led to the development of batteries, which could be used as sources of continuous charge flow. A battery like this was used by Danish physicist Hans Christian Ørsted in 1819 to conduct an experiment in which he hoped to prove conclusively that electricity and magnetism were not related. At first, the demonstration seemed to work. When the switch was closed, the compass needle, which was perpendicular to the conductor, didn't move at all. However, when Professor Ørsted repeated the experiment, this time with the needle parallel to the conductor, and the switch was closed, the compass needle reacted instantly. So it seemed obvious that electricity and magnetism were somehow related. As a result of Ørsted's experiments, French physicist André Ampère made a detailed study of the magnetic field about a conductor carrying a charge flow. Using iron filings, he demonstrated that there was a magnetic field around the conductor. The pattern formed by the iron filings created a series of concentric circles. Depending on which way the negatively charged electrons flow through the conductor, the magnetic field around the conductor will be in one of two directions. With the electrons flowing this way, the magnetic field around the conductor is in this direction. Reversing the flow of electrons doesn't affect the shape of the pattern, but it does affect the direction of the field. Reverse the electron flow through the conductor, and the magnetic field direction will reverse as well. Our left hand gives us a convenient method for correctly predicting the relationship between the direction of the magnetic field around the conductor and the direction of electron flow through the conductor. This is the left-hand rule for conductors, and it states that if the left hand is placed around a conductor with the thumb pointing in the direction of electron flow, the fingers will curl in the same direction as the magnetic field. Reversing the current means that the thumb must now point in the opposite direction. Although the fingers now curl the other way, they nevertheless indicate the new direction of the magnetic field. Of course, if the flow of charge is interrupted, the magnetic field collapses immediately. What happens to the overall shape of the magnetic field if the conductor is bent into a loop? Let's turn the current on again and find out. If we apply the left-hand rule at different points along the conductor, we can map the magnetic field around the loop. Notice that the shape of the field resembles a donut. But if a number of identical loops are added, the resulting figure is called a helix or coil. Looking at the coil in cross-section, we'll represent electrons flowing away from us as X's. And here at the bottom, electrons flowing towards us as dots. Applying the left-hand rule for conductors to each turn of the coil, we can begin to build a picture of the magnetic field around the coil as a whole. Since the distance between the turns of the coil is very small, we might think that the fields would overlap like this. But this is not the case. Magnetic fields do not overlap. Instead, the field of one interacts with the field of the other to produce a combined field like this. If we examine the area between two of the turns, we can see that the two interacting fields effectively cancel each other. This field interaction occurs between each of the turns of the coil, resulting in an overall field which surrounds the turns and resembles a somewhat flattened oval. The same oval pattern is produced at every point around the coil. And it's the merging of all these ovals that forms the magnetic field for the entire coil. Since the field direction of each oval is the same, then in the center of the coil, cancellation does not occur, and that portion of the field is very strong. There is also no cancellation outside the coil, but because the field is spread out, it is much weaker here. The relationship between the direction of electron flow in the conductor and the direction of the field in the center of the coil is given by another left-hand rule, the left-hand rule for coils. This time, the fingers curl in the direction of electron flow, and the thumb points in the direction of the field within the coil, or to the end of the coil that acts as a north pole. The fingers curl with the current, and the thumb points north. If we compare the magnetic field of the coil with the field of a bar magnet, we can see that the shapes are nearly identical. Each has a north and south pole. But an ordinary iron bar has no magnetic poles. What then happens if we insert this bar into a coil with current flowing through it? This compass is responding to the magnetic field associated with the electron flow in the conductor beneath it. The left-hand rule for conductors shows the relationship between electron flow and magnetic field direction. With the thumb pointing in the direction of electron flow, the fingers curling around the wire indicate the direction of the magnetic field. Conversely, if the field direction is already known, the same rule can be used to determine the direction of electron flow. As we saw from Orsted's experiments, a compass needle points in the direction of the magnetic field around a current-carrying conductor. So, by curling the fingers around the conductor in the same direction as the compass needle points, The thumb gives us the direction of electron flow. When a current-carrying conductor is wrapped into a coil, the coil acts like a bar magnet with a north and south pole. The left-hand rule for coils is used to determine which end of the coil is the north pole. With the fingers curled in the direction of electron flow, the thumb points towards the north end of the coil. Since the field around the coil is similar to the field around a bar magnet, can the coil also be used to pick up iron objects? Though the coil is a magnet, it's too weak to pick up much of anything. However, if an iron core is inserted into the coil, the magnetic field strength increases dramatically, and the coil-core combination becomes an electromagnet. This powerful electromagnet can be used to pick up a wide assortment of things. When the current flowing through the coil is turned off, the field collapses and the iron core is no longer magnetic. But just what is it about the iron core that enables it to become magnetized and demagnetized almost instantly? Why is it almost impossible to magnetize copper? And why is it that metals like steel, once magnetized, retain their magnetism long after the current is shut off? For the answers, we'll need to look closely at a typical atom. Nearly all of an atom consists of empty space. Its mass is concentrated in a small, positively charged nucleus. Revolving around the nucleus are tiny, negatively charged particles called electrons. In order to follow their movement, we'll represent the paths of the electrons with circular orbits. The motion of an electron around the nucleus is much like the motion of an electron through a single loop of wire in a coil. As well as determining the north and south poles of a coil, the left-hand rule for coils can also be used to show the location of poles for the electron orbits. Each electron orbit produces a magnetic field with a north and south pole. However, the motion of all the electrons is so random that the magnetic fields tend to cancel each other out. Just so you don't think this is too simple, in addition to moving about the nucleus, each electron also spins on its axis, producing yet another magnetic field. Once again, the left-hand rule for coils can be applied to show the direction of the electron's magnetic field. Two directions of spin are possible, resulting in two different field orientations. Usually, the magnetic fields produced by these spinning electrons cancel each other out, in much the same way as the fields of the electron orbits are canceled. So the net result is that most atoms do not possess an overall magnetic field. Materials consisting of these atoms are not attracted to magnets. An important exception is iron. An iron atom has 4 more electrons spinning in one direction than in the other. As a result, their fields are not canceled or balanced. So the iron atom is left with a resultant magnetic field. Of the common elements, only 2 others, nickel and cobalt, have atoms which are tiny magnets. These atoms are said to be ferromagnetic and are referred to as magnetic dipoles, meaning 2 poles. They can be thought of as tiny compass needles pointing north. In ferromagnetic metals, these tiny dipoles interact with each other, causing large clusters of them to align themselves in the same direction. A cluster of dipoles, which all point the same way, is called a domain. Normally, domains are about 1 millimeter wide and contain millions of atoms, with each domain pointing in a different direction. But when the bar is exposed to a magnetic field, the domains which are pointing in the same direction as the field grow and take over the other domains. The core now possesses a field which is considerably stronger than the original field of the coil. When the electron flow stops, the dipoles go out of alignment and gradually form random domains again. However, with steel, the results are different. The carbon atoms added to the iron to make steel greatly hinder the iron atoms from returning to random positions when the current is shut off. As a result, the steel bar remains magnetized. Even if the bar is broken, the alignment of the domains still remains the same in each half. And so each piece becomes a magnet with two poles. If a magnet is struck repeatedly, the domains may gradually break free of their alignment. Heating a magnet to high temperature also causes the atoms to shift out of alignment, turning the magnet into an ordinary steel bar. As the metal cools, the atoms form a haphazard array of domains. However, if the hot steel bar had been placed in a powerful magnetic field and allowed to cool, the domains would have reformed into a strong, uniform alignment in the direction of the magnetic field. Now, when the current is shut off, the domains remain aligned, and the steel bar becomes a permanent magnet again. But what will happen if we place a current-carrying conductor into a magnetic field? The answer lies in the motor principle. The year is 2010, and on Moonbase Alpha, a shipment of supplies is being prepared for a colony on Titan. The supplies have been loaded into a special pod which sits between a set of rails. A computer closes a switch, and the pod accelerates rapidly along the rail. The force that accelerates the pod was first detected by French physicist André Ampère in 1820. He noticed that when the currents in two parallel conductors were flowing in the same direction, the conductors attracted each other. But when the currents were in opposite directions, the conductors repelled each other. Ampère reasoned that the magnetic fields around the wires created attraction and repulsion forces. The left-hand rule for a conductor predicts the direction of the field around each of the wires. When the fields in between are in the same direction for each of the wires, repulsion occurs. This repulsion is similar to what happens when two bar magnets are placed side by side, so that the field of one magnet is in the same direction as the field of the other magnet. When the electron flow in two wires is in the same direction, then, in the space between the wires, the field produced by one wire runs in the opposite direction to the field produced by the other wire. As a result, the wires are attracted to each other. Again, this is similar to two bar magnets placed such that the fields between them run in opposite directions. These principles explain the mechanism used to launch the supply pod. The launcher, called a rail gun, consists of two rails which can conduct massive amounts of current. The supply pod itself is also a good conductor. When the rail gun is activated, a massive current flows down one rail, crosses through the pod to the other, and returns, completing the circuit. Because of the interacting fields, there is a large force trying to push the rails apart, but they are securely fastened and can't move. The field produced by the current flowing through the pod is in the same direction as the field between the rails. This results in a repulsive force which pushes on the pod. And since the pod is not fixed, the force acting on it is able to propel it down the track at greater and greater speed. The direction of the force on a current-carrying conductor placed in a magnetic field can be easily determined. If the electron flow is in this direction, the field produced around the conductor will interact with the field produced by the magnets. Since the two fields are in the same direction above the conductor is repelled downward. If the direction of electron flow is reversed, then the field around the conductor also reverses. The fields are now in the same direction below the conductor, and so the conductor is repelled upward. This effect is called the motor principle. The motor principle is one of the most important applications of Hans Christian Ørsted's discovery of electromagnetism. But it was British physicist Michael Faraday who in 1821 put all the pieces together and devised the first electromagnetic motor. The motor principle states that if a current-carrying conductor is placed within an external magnetic field, it will experience a force which is perpendicular to both the direction of the electron flow and the external magnetic field. The direction of the force is determined by the left-hand rule for force. Namely, if the thumb points in the direction of electron flow and the fingers point in the direction of the external magnetic field, then an imaginary arrow drawn straight out from the palm indicates the direction of the force exerted on the conductor. Now, if the current is reversed, the thumb points in the direction of electron flow, the fingers point in the direction of the external magnetic field, and the palm indicates the direction of the force exerted on the wire, in this case downward. The motor principle got its name because its first application was in the design of electric motors. A loop of wire carrying a current is placed between magnetic poles. If we apply the left-hand rule for force on this side of the loop, so that the thumb indicates the direction of electron flow and the fingers indicate the direction of the external magnetic field, then the force on the conductor will be upward as indicated by the palm. When the left-hand rule for force is applied to the other side, the palm indicates a downward force. These two forces will cause the loop to rotate about an axis until the loop is vertical. If it rotates past the vertical, these same forces will stop the rotation and return the loop to the vertical position. But to perform work, the loop must continue to rotate. This is easily accomplished by directing the electron flow through a split ring called a commutator, which is in contact with graphite brushes. Initially, electron flow is in the same direction as shown earlier, and the loop rotates as before. But as soon as the loop passes through the vertical plane, the commutator causes the electron flow to reverse. This reverses the direction of the forces on the sides of the loop, which causes the loop to continue rotating. The split ring commutator reverses the electron flow in the loop every half rotation, just at the instant it is required to keep the loop rotating. Normally, we use electric energy to run a motor. But could we use a motor to produce electric energy? Electricity is one of those things we take for granted. We all know what to do with it. Plug this in, plug that in. Oh, we're very good at plugging things in. But it takes a power failure to make us realize how utterly helpless we are without it. The basic principles that led to the development of electrical generators began with the discovery by Hans Christian Ørsted in 1819 that a magnetic field results whenever there's a flow of charge through a conductor. 10 years later, in 1830, the possibility that a magnetic field could generate a current in a conductor became a reality. Working independently, American physicist Joseph Henry and British scientist Michael Faraday performed similar experiments and arrived at the same conclusions. However, since Faraday published his results first, he is credited with the discovery of the effect which is now called electromagnetic induction. Faraday's experiment involved an iron ring and two coils of insulated wire. The primary coil is connected to a battery, and the secondary coil to a galvanometer. A galvanometer registers minute current flow through a conductor, with its needle also indicating the direction of the current flow. Faraday observed that the instant the primary coil was connected to the battery, the galvanometer registered a brief pulse of current in the secondary coil. But, much to his surprise, the needle quickly returned to zero, indicating that all current flow had stopped. However, when the primary coil was disconnected, current was again briefly generated in the secondary coil. Only this time the flow was in the opposite direction. Changing the current in the primary coil somehow induced a current in the secondary coil. Faraday recognized that connecting the primary coil to the battery causes a magnetic field to build up within the iron ring. As the field grows within the ring, it induces a current to flow through the secondary coil. Once the field in the ring is at full strength, it is no longer changing within the secondary coil. The result, no more current in the secondary coil. When the primary coil is disconnected, the magnetic field it produced collapses. As the field in the ring collapses, it again induces a current in the secondary coil, this time in the opposite direction. Faraday's apparatus would today be called a transformer. Experimenting further, he found that the same results were obtained using a bar magnet instead of the primary coil and ring apparatus. One of the most important conclusions from Faraday's experiments can be stated this way. As long as the magnetic field within the coil is changing, a current will be induced in that coil. This principle was used by French inventor Hippolyte Pixii in 1832 to develop the first electric generator. Although it was clear that induced current flowed in different directions, depending on whether a magnetic field was growing or collapsing, why it was doing this was a mystery. 2 years later, German physicist Heinrich Lenz provided the answer. He realized that the induced current generated its own magnetic field. But even more important, Lenz discovered that the induced magnetic field is always opposed to the change in the external magnetic field that caused it in the first place. As the south pole of the bar magnet approaches the coil, a south pole is induced at the near end of the coil. Opposing the forward motion of the bar magnet. The beauty of Lenz's discovery, now known as Lenz's law, is that we can identify both poles of the induced field. And we can use the left-hand rule for coils to determine the direction of the induced current. Remember that the thumb points toward the North Pole and the fingers curl in the direction of current flow. Once the bar magnet stops moving, the field is no longer changing, so there will be no induced current, and therefore no magnetic field. In other words, everything in the coil stops. Now, suppose we begin moving the bar magnet away. Once again, current flows, and a magnetic field is induced which opposes the movement, this time by establishing a north pole at the near end of the coil. The left-hand rule for coils shows that the current flows in the other direction. The principles developed by Faraday and Lenz are applied today in the generation of electricity. The pressure of water or steam is used to turn a turbine connected to a generator. In its simplest form, a generator is an armature consisting of a coil of wire around an iron core, rotating within a magnetic field. The movement of the armature through the magnetic field induces a current in the coil. And according to Heinrich Lenz, the induced current will produce a magnetic field in the armature with its own north and south pole. This field will oppose the armature's movement through the external magnetic field. From here to here, this end of the armature will be a north pole. So at the top, as the armature is turned, this attraction opposes movement away from the south pole, and this repulsion opposes movement toward the north pole. As the armature rotates just past the external poles, the induced current and magnetic field reverse, opposing movement through the second half of the rotation. Again, the induced current and magnetic field reverse as the armature passes by the external poles. Since the direction of the current reverses every half rotation, the resulting flow of charge is referred to as alternating current. And the principle of electromagnetic induction is used in giant electric generators, which supply enough alternating current to keep us tuned in and turned on. An astronaut on the moon is protected from the harsh environment by a carefully designed spacesuit. He needn't worry about the vacuum of space or the extreme temperatures on the moon. But there is another invisible menace which could cause him harm. Exposure to radiation from charged particles flowing out into space from the sun. This continuous stream of matter is called solar wind. And the spacesuit does not adequately protect him from the dramatic surges in the number of particles. More than 3,000 years ago, Chinese astronomers observed dark spots on the surface of the sun. Today we know these spots are actually zones of intense magnetic activity. Sunspots like this one spawn other solar activities such as flares and prominences. Fiery plumes of glowing gas that sometimes surge to heights of more than 150,000 kilometers above the surface of the sun, or 12 times the diameter of the Earth. Each massive solar eruption propels an added burst of charged particles out into space. Since individual particles take up to 2 days to reach the Earth, an increase in the number of sunspots and solar flares acts as a signal to scientists that the solar wind will intensify, becoming a torrent of deadly radiation streaming towards us. Fortunately for all life on Earth, the magnetic field surrounding our planet protects us from this danger. But how? Remember that a conductor carrying a flow of charge within a magnetic field experiences a force that is perpendicular to both the field and the flow of charge. This force will also be present whether the charge is flowing through a metal conductor or even freely in space. Each moving charged particle has its own magnetic field. The circular field of a negative particle is in this direction, causing the two fields to react here. The motor principle dictates that this repulsion pushes the negative particle to the left. However, the solar wind consists of both negatively and positively charged particles, and their fields are in opposite directions. Positive particles, then, deflect off the other way. So when the solar wind encounters the Earth's magnetic field, the charged particles tend to separate, with the negatively charged particles being deflected around one side of the Earth and the positively charged particles around the other side. The result is that most of the particles are deflected and never reach the surface. However, not all of the particles get away so easily. Some become trapped for a while in two large donut-shaped areas called the Van Allen belts, centered above the equator. The inner belt extends 1,000 to 5,000 kilometers above the surface, while the outer belt extends 15 to 25,000 kilometers. Occasionally, particles from these belts filter down to the atmosphere and are guided by the Earth's magnetic field toward the North and South poles. Near the poles, they collide with and excite atoms and molecules in the atmosphere, which release the excess energy as light. In the north, the resulting ghostly light display is called aurora borealis, or northern lights. In the south, it's called aurora australis. Every time there's a display of northern lights, there is a simultaneous display of southern lights. At times, these displays are quite spectacular, visual evidence that a gust in the solar wind has occurred. These gusts, which are the consequence of sunspots and other solar activities, occur in cycles. One theory holds that during periods of unusually low solar activity, glaciers advance and the survival of plants and animals is threatened. But then, with the return of high solar activity, glaciers retreat and life flourishes in a more favorable climate. So far, we've been dealing with the results of solar magnetic fluctuations. Throughout its long history, Earth has experienced periodic fluctuations in its own magnetic field. Geophysicists believe that the Earth's magnetic field is actually produced by complex movements of charges within the molten core of the planet. This flow of charge seems to reverse, on the average about every 200,000 years, resulting in a reversal of the north and south poles. The flow of charge within the core mysteriously slows down, reducing the magnetic field to about 10% of its normal strength. With a dramatically weakened magnetic field, the solar wind is no longer deflected around the Earth, and so the charged particles rain down on the surface. This can disrupt the genetic materials within the living cells. Subsequent mutation may account for the sudden extinction of many plants and animals, and the appearance of whole new species. Then, the weakened magnetic field reverses and returns to full strength. A few species have actually evolved with the remarkable ability to take advantage of the Earth's magnetic field. It is well known that homing pigeons use the sun for navigation. Less known is the ease with which they navigate on days when the sun is obscured. However, in experiments where pigeons were equipped with earmuffs containing tiny magnets, it was found that they soon became disoriented on cloudy days when they couldn't depend on the sun for navigation. When the earmuffs were removed, these same birds recovered quickly and easily reached their destination. Magnetic material in the pigeon's brain somehow allows the pigeon to fly as if it has a compass inside its head. Even microorganisms have this fascinating ability. Certain types of mud bacteria have learned to use the inclined magnetic field of the Earth to determine up from down. In Australia, the field direction is upward, and so bacteria go against the field when moving deeper into the Earth in search of moisture. When these bacteria are brought to the northern hemisphere, they're fooled by the switch in the magnetic field direction and navigate upward instead of downward. This brings them to the surface, where they dry out and die. It's the presence of the magnetic field that originally helped make Earth a cozy planet for living creatures. And it was an understanding of magnetism that enabled those courageous few to spread out and explore the unknown face of Earth.